Hello, and welcome to this session on Oracle Machine Learning Office Hours. Today we're going to be talking about Machine Learning 102 classification, so the next installment of our series on Introduction to Machine Learning. My name is Mark Hornick, and I'm joined by Marcos Arancibia, who will be our speaker today. For the agenda, we'll have any questions that were asked, the upcoming session, and again, our speaker, Marcos Arancibia, Machine Learning 102, and then we'll follow up with Q&A. If you have questions during the session, feel free to add them to the chat, and we'll either address them interactively during the session or afterwards during the Q&A. So for web questions, we actually had just one comment. The previous session was awesome, and I really loved it. I hope that similar sessions will be organized based on different ML functions. And that person followed up with, in the current session, they'd like to provide details about the cost matrix and how to calculate cost and assignments. I've gone through all the documentation, but it does not give you a clear explanation about how cost should be assigned. Also, request you to provide details on model evaluation with respect to cost matrix. And I believe Marcos will be covering some of that today, so stay tuned and we'll hear about that shortly. For our next session, it's going to be June 25th, Oracle Machine Learning Office Hours, 9 a.m. US Pacific. We'll be covering Machine Learning 101, regression. So we'll be looking at all of the different aspects on regression and possibly following that up with a 102 session as well. For product information on Oracle Machine Learning, please go to oracle.com/machine-learning to learn more about the entire product family we have with the Oracle Machine Learning offerings on Oracle Database and Big Data environment. If you'd like to try out Oracle Autonomous Database, that includes Oracle Machine Learning SQL API and later the Python API, you can go to oracle.com/cloud/free. and try out the always free services that are available to you there. So for today's session, Machine Learning 102 classification. In this session, we'll pick up where we left off from our 101 session, go deeper into discussions on ML algorithms, the importance of feature selection, and explore even more the correct way to evaluate models using the confusion matrix and the many statistics that can be computed from it. So without further ado, we'll pass it off to Marcos, and he'll take us through today's agenda. Thank you very much, Marcos, for being here and telling us about all this.
Thanks a lot, Mark. Thank you. Hi, everyone. So I just saw one of the questions actually being posted, I think, on the chat, asking about the recording of the last session. And yeah, so the recording of the last session is up, so you can go back to the same office hour site, and the recording is there. So for today, since we saw all of these different components, right, the last time, for today, I thought we would go back to reviewing a deeper notion on the confusion matrix, like we were talking about before, but now understanding a little more of the kinds of things we can see and we can do when we talk about a confusion matrix. So to begin with, we can start by, a quick review, right, on that confusion matrix. So remember that we were talking about, the idea that if you're doing a classification, you want to make sure that your model is good, right? Your model is able to identify the events, right, that you're trying to find, but also that the model is able to identify the non-events. So in this case that I have here on my screen, you see in the case of the events here, I have 20. My model was able to find 20, right? He predicted that there were going to be 20 here, and 20 were good, but also he thought these 12 guys were part of that prediction of good or my actual target customers, and they are not. So this is a mistake that the model is doing, right? But then we also learned about the other mistake, right? Which is the model thinks that this guy is not a responder, right? This guy is not your target when it is. So what the problem with that is that notion of having these two types of errors, right, that would actually get balanced, and you need to make sure they are balanced, right? If you create a model that is able to say, I am able to almost get every single good customer, right, on my entire data set, but by that, I mean 80% of the people that I'm capturing is a non-responder, then the problem is you're contacting too many people, right? So the problem there becomes you got a great model that can give you, a great precision, because then at that point you fill this up, right, almost entirely, right, and you almost have none down here, right? So you could have 100 here, one guy here. So the precision is great, right, of your model, right? 99%, amazing model. But the problem is down here, you might have, 800, right, records. And the problem there is the only way you can see clearly this is not use just precision, right? Using the accuracy. Accuracy then takes into account all of the entire confusion matrix and shows you that, right? Today, we're going to actually see many more measures, right, of quality on models as well. So again, to give you a good perspective, I urge you to go back and take a look at Wikipedia for confusion matrix, right? There is a lot of things to do there, and there's many different links, right? All of these kinds of things are sublinks that you get when you go into Wikipedia to understand exactly what those things are. But at the end of the day, there are a few things that are very effective and efficient for you to look at into a model and be able to say, this is a good model, or this is a better model, or this is a worse model, right? So those things then, at Oracle, right, we have done a lot of work on that on many different tools. So to give you an idea of the theory first, I'll show you that in our SQL Developer tool. So inside SQL Developer, you have the Oracle Data Miner, and the Oracle Data Miner does do a good job of graphically showing you what we call a lift or a gain chart as well, right? And when you think about this, right, you look at this chart, and the idea here is we want to be able to compare models and compare model quality and try to understand what the models are doing, right? So in practice, what this model is showing you, right, because we're looking at cumulative positive cases per model. So you're taking the model, you're taking the probability that the model is telling you that it thinks that this person is a case, or this person is a target, and then you sort all of these columns, every single probability of the model, you sort it by the probability in descending order, right? And then you slice in the bottom here, you have the percentile. So you're slicing this axis and saying, okay, for example here, right, what I'm saying here is, in a cumulative way, by the time I hit 20% of the customers that model told me were going to be good, right, then what this chart is showing you is how much of the percentage of the entire set of positive cases would I be able to capture. What it shows to me is, this guy, if I took 20% of the top people defined by your model as a top probability of being a case, right? I took that cut, 20% of that. And then what I'm looking here, and I'm able to capture almost more than 0.5 or 50% of all the positive cases, which means I'm saving money, right? If I was just offering something, I'm saying, okay, with only 20% of the budget that I originally would need to contact everyone, I'm actually able to contact 50% of the responders, okay? So that is good, right? That is not perfect, because the perfect model, as you can see on this green line here, right? The perfect model means, okay, if my model was really, really perfect, I would be able to identify every single respondent right away. So basically what it's telling me is, you know what, with only like 2%, I would be able to get the entire set of my positive cases, because in this case, I might have a proportion that is 0.2 or 2%. So only 2% of my data set are responders equals 1, right? So that means, okay, my model has a long way to go, right? My model is trying to get all the way there, close to this line, right? That is the perfect line. On the other hand, you have the random, right? The random means I don't get any model, right? I just take a coin and flip a coin and say, whether a customer is going to be good or not, right? So that is 50-50. So if I just said I don't have any models, right, you would expect that with 20% of the customers that you get, you would get 20% of the response, right? With 40%, you'll get 40%. With 60%, you'll get 60%, right? Because you're randomly picking up people. So at that point, you don't have any model, right, to use. Now, you see that all models, of course, converge to 100%. So that means the model that comes here the faster is probably better. But then you got to evaluate how much you actually can do with this model, right? In terms of the quality of the model and in terms of your budget, right? Because if you're thinking about a marketing campaign or you're thinking about that kind of process, you'll want to limit the budget, right, to that certain point. So this is the classical percentile, right? Cumulative positive cases that you can see that chart. And basically what we allow you to do inside the SQL Developer UI, right, is that you do get that kind of capability where you can see then the lift, right, the gain, cumulative gain, which I was saying before, right, with 20% cutoff, my best model here, the green guy, right, the SVM model, is picking up 52% of the total responders, right? And then you see this lift value, right? So the lift value means how many times better is this model over the random model, right? So the lift of 2.6 mean this number, 52.7, is 2.6 times better than just 0.2, which is the random model here, right? Now, if you don't look at that cumulative cases, we also offer in that tool the other chart, which is the cumulative lift, right? And the cumulative lift, again, is also an interesting model. It's going to show me the capability of each model, right, at the top end here, right? So they're starting over on the top here, and then they have a fall off, right? The cumulative lift of the perfect model is always going to be all the way up high, and then it's going to fall off straight out, right, to 1, because at that point, I don't need to capture anymore, right? I captured all the customers I needed. Some of the other models are going to have a good lift, but then you can see that by the time you cut off at 20%, you're saying, well, my model is, as we said before, 2.5 or a little over, right? 2.6 a lift, right? Better than the lift of 1, which is random model. But of course, at the end of the day, if you go all the way to the right, everyone is at 1. Because if you choose to contact everyone, then you no longer need a model, right? But then you get 100% of every responder at that point, right? You would have gotten 100% of the responders, right? Now, because this is looking at the past, you notice that I'm saying you would have gotten, right? It's important to notice also that everything you guys do in machine learning, all the models, we're looking at this in a retrospective way. Any changes in the behavior of your problem, right, of the people that you're looking at, may affect the quality of the future model, right? So no matter how much you train the model and you study and you stabilize your model, right, it is only when you score and run it in real life is that you're going to see the actual capability that the model has, right? So normally you would actually put these models to run and deploy them, right? And then compare them with previous models and compare them with better models, and you keep iterating over it, right? I like to say that a machine learning algorithm, right? It's not, there's never an end on how much you can improve on an algorithm, right? There is always, you start that model, you decided you want to do a campaign, you start that process, and that process is, as we saw before with the CRISP DM methodology, right? It feeds back, right? It's a loop that comes back and you work on it. Having said that, and related to the web question, right? So inside the SQL Developer Oracle Data Miner tool, we actually created the ability for you to just click and create and analyze a profit chart, right? What that means is this chart gives me an idea of, I can change the values there, right? Because right now everything is 1, which means the entire confusion matrix has the same weight, right? If you remember the confusion matrix that we were talking about before, when we talk about it back here, right? When I was talking about it, I was saying, okay, the costs might be different, right, between this error and that error, right? If I don't care how many people I hit, and I only want to, hit more and more people, then the cost of this error is low, right? But if you are talking about more critical things, right? Maybe it's a sickness, maybe it's a fraud detection, right? Then I don't want to increase this number too much, because my model predicted that this guy was a good transaction. In fact, it was a fraud. So then this is going to cost me. So if I'm a bank, I really want to keep this guy low, right? I am interested also in keeping this one low, right? Because I don't want to stop people from buying too many times, right? Because I will annoy the heck out of people. So if I start increasing this number too much, then I'm going to get a lot of calls to my call center because people are getting frustrated with their credit cards blocked, right? And then, so I want to control those two. But which one has the most cost, right? So at that point, the bank has to decide whether the bigger cost is this one versus that one, right? And probably is going to be this one, right? Depending on, especially on the type of credit card that you have, right? If your frauds are typically very low money, but annoying a very good customer makes them leave, then you will want to balance these things. So only the business person looking at this will be able to decide how much value to assign. But in our example here, right? Let's say the marketing example works very well here. So for example, a startup cost means I have a base cost for my campaign, right? I have a base cost for all of these people that I'm going to run a process on, right? And I have a cost of contacting these people. So that's my startup cost, right? It's going to cost me $1, right? 50 cents is going to cost me how much money do I have to pay for a lead, whatever you know in your industry that works. So you have a startup cost there. But then you have also an incremental revenue, right? Which means if that customer accepts, right, it takes my call, or it clicks on my and it buys my product, right? How much of that money is incremental compared to a customer that did not click on that, right? So then you get an incremental revenue. You also have an incremental cost, because there is a cost of processing, right? So I actually have, if the customer accepts my offer, right, I might have the incremental cost. I have a welcome kit, I have a free shipping offer, I have something that's going to cost me, but I'm trying to engage with that customer, right? And then finally, most of the people have a budget, right? So most of the time you will have a budget, and if you insert a budget here, you'll get a line saying, okay, up to this point is where your budget would allow you to do, right? So it doesn't matter if you like your model down here, if your budget only allows you to get 5% of the population, right? And also the number of people. You might have a limit on number of people, right? So you might say, I actually only built 10 of these special mice that I'm shipping to people, right? I built 10,000 of these, right? So I cannot contact and offer 100,000 because I just don't have that to ship, right? So having said that, then this is the place where you have all of these interaction happening, right? So the SQL Developer app and the Oracle Data Miner inside it has all of these interactivity and allows you to do that very easily. We do have the cost matrix coming to actually part of the Oracle Machine Learning for SQL, right? That runs inside the database. And I will add that capability to show you examples in the Oracle Machine Learning for Python notebooks that I prepared for today, but I did not prepare the cost matrix yet in there. But I just wanted to highlight to you that this is all happening in database. It is doing all of those computations for you. So you will have, you do have today a place where you can specify the cost matrix and then execute it, okay? So with that said, what I did for our demos and deep dive is I actually did a Decile gains chart, right, or lift chart for our example, right, in if you remember the example we were using before was the breast cancer example, right? Whether the cancer was a malignant or it was a benign. And what happened there was actually the proportion of malignant tumors that we had to evaluate was actually 0.6 something, right? So it was almost 70%. So what happens with that is then the idea is that in the 7 top deciles, you will have actually tumors detected, right? Or malignant tumors. So what I did in this chart, right, is basically the steps are on the right-hand side here. So again, you sort by descending probability of being a target, right, or being a malignant that was decided by your model, right? You divide that data into this percentile. So you slice them, right, into 10 in this case. Or if you were using percentiles, you could slice it in 100. And then you evaluate on each slice the proportion of how many corrects you got. So the model was doing well here, right? On the top decile, it was doing okay. But then you got down here to the deciles 5 and 6, and you can see that the model could not, right? The model was unable to detect, 9% of the malignant tumors over here, right? And he was unable to detect 4% of the malignant tumors over there. So that's what a normal model will do, right? And then after decile 7, right? Because you can see the ideal is done here, right? By the time it gets to here, right? Deciles 8, 9, and 10 are just errors, are complete errors by the model, thinking that this was a malignant when it was not, right? So that's the other error, the tail end of that. That is a one simple way of doing this. I looked over all the different types of codes that people have done. There are many packages in Python that do these kinds of things, that can do these automatically. But I came, I would say, underwhelmed by what I saw in terms of availability of all these types of things, right, that can be plugged into your projects. In any case, we're going to look into that code later. So the other chart that I thought it was interesting to plot was a histogram of the target versus non-target, right? So if you think about, again, our example, benign versus malignant, what you want to do is you want to plot the density, right? The distribution of the predictions. So you say, okay, I have here then in blue, I have every cell, right, that my a sample that my model found to be malignant, right? And this is the probability that the model thought that this was malignant. You can see that there are a few that were actually malignant, but my model gave it a very low probability, right? So the actual ones and the actual zeros, right, which is the real truthful malignant and benign, but my model, for example, scored a few of these benign tumors as malignant, right? And you can see them in here. Those are the yellow that came across this line. So this line is basically what you call a cutoff point, right? And normally, depending on the models, especially if the sample is balanced and all of that, you would get, say, a 50%, right, 0.5. There are many proofs out there that say that the best power for these models to separate good and bad happen when you have this 0.5, because you have a good range to work on when the original probability is that. In the real life, your cutoff point, right, if you think about, how to choose a model, right, and you have only 1% of responders, right, then your model is trying to create this distribution around that 1%, right? So the probability can be still the same, but let's say the specific rate, right, I'm looking at is churn versus non-churn, right? Fraud versus non-fraud. But still, I want to try my model to create this 50% cutoff point where I can actually better evaluate the model. Otherwise, if you didn't balance that, right, and those are balanced by default by Oracle's in-database algorithms. But if that wasn't balanced, right, just imagine, right, what is a model if I have only 1% target, right? If I have actually, yeah, I have 1% target, right? I have 1% fraudulent transactions, right? What is a model that will tell me with 99% confidence, right, that the transaction is good? A model is a non-model, right? A model would be, there is no bad transactions. The model will be right 99% of the time, right? So that is the question. That's why you work with these to stabilize that sampling. So usually you will do oversampling and adjust that to a 50-50 split so that the model can work on that and adjust that and compare that in a more fair game, right? So that at that point, you want the models to offer an effort, right? Put an effort on it. So that's basically in layman's terms what that means. So that is a good chart for us to evaluate. Also, the next one is the receiver operating characteristic curve, or ROC chart, or ROC curve. And basically what this guy is doing is he's plotting the true positive rate against the false positive rate, right? So again, you have the famous random guess, right? Which means, you know, there's no model. Your model is unable to identify a true positive versus a false positive, right? So your model is not able to grow up in this curve, right? But basically, this also known as sensitivity, and this acts as in 1 minus specificity. So if you are a statistician, you would probably learn about those terms, right, first. But normally, that's basically the idea here, right? You're trying to get as close as possible to this top one here, right, and go a straight line over there, which means your model is perfect, right? At this point over here, your model is the ideal model, right? You got all true positives without getting any false positives, right, at that point. So at that point, it's amazing. And then you got all of the false positives we got without moving your true positive rate. So that would be the ideal world, right? But we imagine normally it's never that easy. In any case, there is an optimal cutoff point, which usually is where you got a maximum of both the TPR and FPR, right? The true positive and false positives. But in any case, one of the statistics that is very widely used to compare models is the area under this curve. So the area under the curve, usually known as AUC, area under the curve, means actually area under the ROC curve, right? It's just that the name would be so long here, wouldn't be fun. So the AUC, the area under the curve, is very much used to also compare the quality between models. So when I was coding this, what I did was I ended up adding some statistics right there, right? So I said, you know, let's add some model quality statistics inside this area, because this area is always empty anyway. You're not going to see the curve coming down this way. So that's a good place for us to put some statistics anyway. Okay, so based on that, also, when you think about the relationship, right, between everything we were looking at, we can see there is a relationship between the cutoff point, right? Remember the distribution chart where we had the true negatives and a true positive side. But there is also that mistake, right? The mistake that my model was doing, right, at that point. So that mistake where I had some false negatives, right, and then some false positives, right? So all of that process is basically coming from here, and this coming from your confusion matrix, and also that affects the ROC chart, right? So everything is interconnected here, all these proportions. So if you move that cutoff point here, it means you're moving this guy here, so you're letting more false positives come in, but maybe because you don't want false negatives, right? Depending on your problem, right? You don't want false negatives, so you want to make sure that your model capture every single transaction, right, that was going to be a fraud, right? then you're very worried about these false negatives. So you might pull this guy over to the left. You're going to increase the number of false positives, right? Remember, you're going to stop more transactions from coming that were actually good. But, you know, if you're risk adverse and the risk is high here, right, then you want to stop this from happening. So you pull that cutoff point back, right? So all of these things affect how each other works, right? And they are all based out of the confusion matrix. Okay. So before we move on to the demo, or I think I'll leave the questions. How are we going with the questions, Mark?
We're doing rather well. We've got a couple that are queued up here. Some that were focused on the Oracle machine learning notebooks availability. When will OML for Pi be available, et cetera. But I think we're doing quite fine on that. So if you'd like to continue with the demo, I'll answer a few of these online, and then we'll take questions at the end.
Okay, perfect. All right. So the idea, just like before, right? When I was presenting this to you the last time, right? I was going through the step-by-step here. So the idea was, okay, we're going to look at data set, right? The same breast cancer data set we used the last time. But we're going to do, for this time, we're going to use more columns. We're going to use all columns, right? So I have initialization of the environment. I have, of course, the Python libraries I need to load here, right? So I need to import the AutoML and the OML, right, libraries into my my environment. I don't need to connect to the Oracle database when this product launches, as I mentioned before, right, in Autonomous. You will not need to connect to the database; it's going to be already there. Right? Now, as before, we load the data. So I'm loading the data into from scikit-learn. I'm loading that data locally, and then I'm pushing that data to the Oracle database, right? So right now here I am pushing that data to the Oracle database, and then I can see that I am dropping, right, at any table if it's available, and then I'm pushing that data with an OML create, and I'm pushing the entire data set there. So I can see both now the data set, so all of these columns. The last time, in the last lecture, we used only 2 columns. This time I'm using all of the columns available. So all of these different types of columns that were already processed, right, pre-processed in terms of the mean of all of these masses that were being analyzed, right, all of these cells. So, and you can get statistics on all attributes as well, right? So we'll use all the data sets with the binary target column. We're going to always remember splitting the data, right, between training and test. So in this case, I'm splitting that in 60%, right? So I'm doing a 60% for training and 40% for a validation, right, test. And then we can build several models. So I want to show you guys this this code, and then I'll show you what it does, right? So what I did this time, instead of building model by model, right, I'm using now a function. So you can just pick up, you know, and create a function in Python, right? And basically, this first function I'm doing is I'm going to say, you know what, I have several types of models, but most of them you know, specify the same things. I have a model, right, a model type, and I have, or the model function, right, if you will, and then you have some settings. So I'm putting some defaults here. So by default, if you give me nothing, I'm going to run a decision tree with a depth of 3, right, and I have a name of that model that I'm going to use for charts and things like that. And then I have the train Y, right? So the train X and the train Y, and then I'm passing up the test, right? So in this first portion, right, and I'm getting the target variable, right? So in this first portion, all I'm doing is I'm really literally building the model, right? So I'm gonna take the model that you gave me, so machine learning decision tree, for example. I'm gonna pass it the settings, which are these ones, and then I'm gonna fit the model. So I gotta fit that model with the trained data. And then I'm going to predict the model on this test data, right? So what I'm doing here, I'm predicting that model on that test data set that you passed me. And I'm also staying or keeping the original target variable because we need to compare it, right? When we're doing the statistics, right? So I'm passing to you, I'm receiving back, right? Not only the probability, the prediction, right? But also that the original actual response, right? Benign or malignant. But now I'm giving you another option. The last class, I remember there was many questions about probability. So if you do proba equals true here, when you're building a model, then you're also going to receive probabilities, right? But the probability that you receive here is the probability of that decision, okay? And that makes sense, especially when you're doing multinomial models, when you have several types of classes that you're predicting. You want to actually get what is my largest probability so that I can get the class, right? But in this case, all those charts that I was talking about right before are basically constructed using the probability of one, right? That's one of the columns that I want to use. So what I'm doing here is I'm picking up the probability of one, right? Which is the probability of malignant, right? That's my target. And with a simple process here, with a simple concatenation here, I can actually pick this up. And remember, this is all in the database, right? So I'm still using these proxy objects to the database. So the database is the one doing all these computations and all these aggregations. And I'm here comfortably in Python, just coding away, right? So with this little code, what I'm doing is I'm getting now a new column called probability of one. So what that means is now if my decision was for the 0, instead of getting a higher probability because I decided 0, I am getting the probability, say 40%, right? And then from then on, I have that monotonous descending probability all the way down to 0, close to 0, right? Whatever my model decides. So with this little function, I'm returning the model object itself, and I'm returning that prediction of data frame, right? So the prediction data frame here contains my original prediction, 0, 1. It contains my target because I asked it to keep the target. It contains the probability of my decision, and it also now contains a new column called probability of 1. Okay, so this simple function helps me with that, right? And it's very simple, very easy. Now, on top of that, I created another function, a separate function that called evaluate model. So this guy feeds from, and it needs a prediction, right? Exactly like that. I need a prediction data frame, right? I need a settings name. Is just for the printing, really. It's just for showing that in a table at the end of the day, and the name of that model, right? Just for showing that in charts and in a table. But I need the target variable as well. What I do with that then is I'm loading a few packages. I'm actually only using these 2 packages that are part of the scikit-learn metrics, right? So Oracle Machine Learning for Python in Autonomous includes the scikit-learn. So I'm including that in the metrics there. And I'm using matplotlib as well, which is also included, and numpy, which is also included. So I can call these functions from the packages that I'm using. First step that I do is create a confusion matrix, right? So if you guys remember the last time we were doing this cross tab, right? Again, this is still an Oracle table. I'm doing a cross tab. This is transparently translated to the Oracle database. It comes back with the results for my confusion matrix. Now that this confusion matrix is small enough, I can pull it in memory, and I now, by location, I find the true negatives, the true positives, the false positives, the false negatives. And with that, I can actually create straight out the rates, right? The rates, or the true positive rates, the false positive rates, true negative rates, and false positive rates, which is based on them plus, some of the specific parts of that confusion matrix, right? On top of that, I can, of course, compute precision, right? I can compute accuracy based on that. And I have many more, negative prevalence as well. I can do detection rate. So these are all statistics that are based on, a few of the combinations of that, right? And balanced accuracy as well. Now, there is a way to compute the AUC via a triangle, right? I would say it's not super precise. It can be used, and so you can, if you want to not have to bring the data locally, right, and use all of that power of the data locally in Python, and you just want to get a rough estimate for AUC, you can compute it right with that. And that is part of that process that we were talking about before. And the reason is because if you look at what this curve looks like, right? What that would be doing is that would be creating a triangle between this point and 0, 0, and that point and 1, 1. So that triangle plus these other triangle here would give you a rough estimate of that area, right, under the curve. Again, it's not precise, right? So I wanted to actually enhance this process. So I actually then pulled the prediction data locally, and then I ran this ROC curve that is part of the scikit-learn metrics package, right? That's a function, comes with that package. And then I'm passing the target, and I'm passing the probability of 1. And that guy now gives me the also the area under the curve using the AUC function, specifically based on these vectors. Now the FPR and TPR are vectors that I'm going to use actually for my plots as well. Okay. So also on that, I'm adding an F1 score. The F1 score is also a measurement very used. The good thing is it actually uses precision, but it also uses the true positive rate, right? So it actually balances out a little better the confusion matrix as well. So it's I would call it a more balanced than a raw precision metric. And the Matthews correlation coefficient is also a very interesting measurement. It's a little more stable and more newer than all the other measurements, but it's also been used and proven to be very stable to show and compare quality of models, right? So I said, why not, right? Because we have these numbers already. So it's definitely easy for us to just compute all of these things. So all I'm doing here now, I'm storing all these statistics on a vector that I'm going to pass into later into my models, right? Now, we are using Zeppelin, right? And Apache Zeppelin has these funny things that it allows you to use something called a percent table and print out this in a better way, in a better looking way. So if you want to present things, right, to customers and to your project, so normally you could, by the raw presentation of Python would be just a plain numbers, right? So you get this plain numbers that is an output of looking like a terminal from the 80s, right? And that is not super beautiful, right? Depends on what you're showing. It doesn't show well. So I said, you know what? We can actually get a nice print, right? Because you can get the round the numbers, right? And then you can actually, and I call this the true negative for printing, the false positive for printing, because I rounded the numbers here. And you can actually use the print function in Python with this percent table. So you will get this a very nice, you can separate each column with this /t, and you can separate each line with a \n. So you guys will see how that looks when we print it out, okay? Continuing on, then I decided to build the 3 plots we were talking about for evaluation, right? So the first thing was a lift chart. So I won't go into super details on all of these, but basically remember when I was talking that you need to sort, right, the values by the probability, descending, right? So ascending equals also in the descending way to compute that part and split out, right, the deciles, right? Split out the data into 10 slices, and then I'm grouping by that decile and aggregating the count and sums of that probability of 1, right? Then I do the ideal, so the best model, right? So the ideal model, I sorted by target now this time, right? 0, 1, ascending, false again, and I do the same thing. So then I plot, literally I'm only plotting bar charts, right? So I'll plot 2 bar charts, one for the ideal, one for the target. I'm giving it dark orange and blue colors, okay? This might be useful for you guys as well. You can be probably more mindful of colorblind people, right? So you try to use colors that would mix better for the people in your charts. That might be a good idea. So then, basically at that point, we get the output of that, right? That process, and here I'm just producing the labels. So I'm printing the labels on top of the charts to show the percentage, right? The second process is the gain chart. For the gain chart specifically, I'm using the probability of 1, and in this case, remember, I only wanted to print that histogram, right, of that probability of 1, right, with the density, and using, you know, a set number of bins, right, and with the color. So I'm printing that on my blue for my target equals 1, and the dark orange, right, which is the probability of target equals 0. So again, the idea is very simple: probability of 1, density to compare, and this axis, this is a vertical line on 0.5, right? And also the ROC chart, right, at this point is the curve, right? The curve, the ROC curve, that I'm using now the vectors FPR and TPR that I computed before, with all of these annotations that are helping me specifically remember that I wanted to print all the statistics inside, right? So again, very simple functions, and all that do then now is I can just call, for example, right, I can call a decision tree, right? So I can call my decision tree with a tree depth of 2, for example. I give it a name, right? And then I capture the prediction. So I'm returning the output and the predictions, and I am actually storing those predictions into lists, right? So I initialize a local list, right? And in pandas, in this case, a local list is a local pandas data frame where I'm going to accumulate the statistics for every model, right? So that I can compare them afterwards. And remember the beautiful printing, table printing, this is what it is. So I'm actually able to control what goes in each place here. So I can print confusion matrix, actual 0, actual 1, predicted 0, predicted 1. I can see the true negatives, false positive, false negative, true positives. I can put things like the actual number, and I can put a percentage inside, right, in parentheses. So you get a much more control by exactly how, you know, how nice you can print out the table, right, in Zeppelin with what we did. And also I can print out statistics down here, right, accuracy, AUC, and F1 score, right? So for that model evaluation, you can see the model down here. So that's the statistics, right, out of that model. This is the result of that. And basically you see that, well, I could have used the triangle for this one because the decision tree is very specific, right? So it's got some cutoff there. So to look at the model itself, then, depending on the type of model, you can see different things, right? With a decision tree, you can see things like the parent nodes, the cutoff, where the node was cut, and these are all inside the model objects themselves, right? So the model objects will give you things like the split. So you see what were the variables that it used, right? It used only 2 variables. It used the worst perimeter and the worst area, right? These were the cutoff, and actually the split was just the worst perimeter, and the surrogate was the worst area. So you see, it's part of that model object, right? Is dot nodes. I can see that, and on the right-hand side, I can see the splits, right? The distribution of the splits that each of the nodes have now in terms of the targets, right? So again, I repeat that process for several different decision trees, right? Nodes equal 5. I get an even deeper down. I get naive Bayes model, so I can see it's looking much better now, right? It's able to separate this well. And naive Bayes can give me things like this, which is the output of that attributes and all the conditional probabilities that the model decided, right? For every variable, right? How the model decided whether it was a malignant or a benign, right? And then that's what it's giving me. A logistic regression algorithm, right? That will return exactly the probabilities now in this case, that same slices, but the return of that model is now the coefficients. So I can see the coefficients that the logistic regression in this case gave me, right? The estimates of that coefficient. And I can see the quality. So some of the model quality comes out of that model directly, right? So I get all of these outputs, and then I get all the way to pseudo R square and things along those lines, right? That these models have. So again, depends on the model, it's going to give me statistics. And I'm going to come back to that real quick. Again, with feature generation, so I can say, hey, I'm not only want to do my model, I want actually the model to generate features. So I can do feature selection and I can do feature generation, and then the model builds that. And now the model is now changing that, right? So the model can now detect and say, you know what, the model now, even though it might be as good or better than the previous one, is now only using three variables, right? A radius error and an interaction between the worst area and the mean compactness, right? So this interaction variable was created by the decision of the model. It tested all these interactions, right? And then it decided by this guy. So again, every model is going to have its own things that you can add and change. Random forest is one that actually, by its nature, returns the attribute importance. So I can see the name of the column and the attribute importance, so I can compare the attributes and see which ones were the most important. But I will note that by the time AutoML4Py gets to production, we are going to have a methodology that actually will give you the capability of getting the attribute importance for every model, okay, through a simulation. We're coming out with that. I was unable to get it done for this demo for you guys, but it's going to be in the final product, and I'm going to add it to this notebook so that you guys can use it and see it. So continue with a more random forest, and you can see, the deeper you go, now I have 100 trees, right? So this guy's looking good. But then you can overwhelm that as well, 500 trees now. So the problem now is the model gets too specific and I start losing that quality. So I now go to support vector machine. So the linear kernel will show me the attributes, right? And the values of those attributes. So with support vector machine, I got some attributes that are attribute names. I can see a listing of the attribute names, right? But when I go to something like a Gaussian kernel, then that guy's not going to give me anything, only a list of the attributes that were used. But you can see this is amazing, right? This Gaussian kernel is just an amazing model, right? So you can see all the way where it went there, right? So this is an incredible model, right? And I added a complexity factor, right? So you can play with those things and you can try to customize them a little bit. So I customized that. I added a factor to that, and then I can see that complexity factor here, right? And I added that into that process, right? So in any case, I also have neural networks. They also are very good, but when they make mistakes, they make big mistakes, right? You can see the probabilities are actually jump around very strongly in this case, right? And then I can improve that. So I got 2 layers of neurons, right? One layer with 4 neurons and one layer with 2 neurons. That improves things a bit. And then now I got I went too far. I went 3 layers with 8 neurons, and 2 neurons, and that came worse than the previous one, right? Because now I started getting a lot of errors over here. So at the end of the day, you can compare also the AutoML, right? So the AutoML, remember the AutoML, we can also do that same process. You can have feature selections for it, and you can evaluate the AutoML models. So if I did not touch anything, would the AutoML model give me, good perspectives, right? Good output. So it gave me a good neural networks. Then it gave me a good ridge regression, and then it gives me a good, decent Gaussian, right? SVM Gaussian. So the good thing with this script that I created was that you can actually get a final summary. So you can see all of the models and compare all of them and sort them by whatever you want, right? I can sort them by accuracy. I can sort it by F1 scores. And I was adding that settings just so that I could remember what were the settings that was adding, right? So I have an AutoML with this or random forest with that, right? So you can see basically that's the final comparison of the models. So in addition to this, I have still the prediction of every model in columns that I can use for increased charts and improve the charts qualities that I want to be able to play with. So we are at the top of the hour, so I just wanted to give you time to get your questions across. Mark, do we have questions in the chat?
Yeah, I think we're caught up on the chat for the time being. With the question that came up is where can we get a review of this example script? I mean, because Python isn't released yet, OML for Pi isn't released yet, we can't necessarily make the notebook itself available. However, it is part of this recording, which we will share on the Office Hours channel. So as soon as OML for Pi is released, we'll be providing a large number of resources available for people to see how to use the API and many of the examples that Marcos has provided here. There were a lot of questions surrounding OML for Pi in the Q&A window. And so we've addressed most of those at this point. One of the big questions had to do with when is it going to be available? And right. Certainly it is. We're all asking that question, right? But it will be coming soon. That's all that we're allowed to say at this point. But it is indeed coming soon. So we actually have been working with the pre-release product, and it's coming together rather well. So we're looking forward to giving that to all of our customers and users. Excellent. Where should we watch for the release announcement for OML for Pi? That will be on the blogs for Oracle Machine Learning. We have the general Oracle Machine Learning blog, and there also will be a blogs.oracle.com/Python, where we'll be posting blogs there. So you can look there for an announcement. How do we choose to, how do we intend to get to data science AutoML visually? Ah, that's a very good question. So certainly AutoML is available in the Python API, and there's interest in making that a code-free interface so that users can get the benefit of AutoML without actually having to write any code. And this is something that we are also releasing soon, referred to as the OML AutoML UI. And within that, it will make it very simple for users to specify the input data set that they want. They'll need to have prepared it as they would like prior, but then it will automatically go through and test the various algorithms and select the model for you, or you may select from the set of models that it provides to you on the leaderboard. And there will be other functionality that is available there as well. Are there any specific use cases where OML for Pi would work better than data science or vice versa? Well, certainly this is a very interesting question, and we do receive this a lot, is, what is the, I guess, the sweet spot for each of these products? Well, really, they're very complementary in nature. If your data is in Oracle database, and the types of models that you need to build are available in the kernel of the database, then you get the performance benefit and the ability to deploy very easily those models and keep all of that within the database environment. If your data is, say, principally on the, say, cloud storage or third party, and you have no intention of bringing that data through Oracle database, then that would be a case where certainly data science makes a lot of sense, or that you want full access, at least initially, to the Python environment. One of the questions that was in the chat earlier was, does OML for Pi allow users to install their own packages? And in version 1.0, we'll be focusing on the in-database functionality and a select set of packages that we have available with the release. So OCI Data Science would give the Python user access to a broader set of packages at that point. So I think there are some trade-offs there that users will have to keep in mind. Another question, for data quality and data analysis in Autonomous Data Warehouse, the customer will need to do that by scripts in Python, or data mining in SQL Developer will be released in the future for Autonomous Data Warehouse. At the present time, our roadmap does not include Oracle Data Miner itself access to Autonomous Data Warehouse. So in the sort of near term, yes, you would look to leveraging some of the functionality from the Python environment in order to do some of what was being done in the Oracle Data Miner user interface. Are there any example data sets we own and can use internally? How about for product demos? I take that this is an Oracle-specific question, so please reach out to us by email, and we'll be happy to point you in the direction for a lot of those types of resources. Okay. I think that largely covers it at this point. So if there are no other questions, thank you, Marcus, for a very exciting talk, as well as demonstrations and all the functionality that was there. And we'll look forward to the next session coming up June 25th, which will be on regression 101 for machine learning.
Perfect. Thank you very much. Thank you, everyone. Have a great day.
Take care now.